Good
Morning,
morning, Dr. Sandeep.
sir.
How are
We'll
you?
wait for another 5 minutes. Let other participants to join. Should we wait?
Yes. Sure. Okay.
So should we check that you are able to share your screen? I think we're giving you the rights to share the screen.
Just a minute.
Okay.
Yes, I can share. I have seen.
Okay,
This
sir.
option
We'll
is available.
start after 5 to 7 minutes. We'll just wait.
Perfect. Okay.
Okay, sir. Thank you. Uh, Good morning, everyone. On the day 4 of the STTP on artificial intelligence and machine learning with data science. Myself, Sandeep Kumar Singla, Assistant Professor, Department of Information Technology. Welcome you all on the day 4 and welcome our expert of the day, Dr. Partha Pratim Roy from IIT Roorkee. Now I invite Professor Siddharth Jain to introduce our guest of the day to all the participants. Siddharth sir, please.
Good morning. Good morning to all present. Good morning, all participants. I am Siddharth Jain from Department of IT, GNE, and I am having great privilege and to welcome and introduce our guest speaker for today. Our speaker is Dr. Partha Pratim Roy, and he's Associate Professor in Department of Computer Science and Engineering from IIT Roorkee. His educational qualification includes he has done his MS and PhD from University of Barcelona, Spain. He has also she has done Bachelor's of Technology from Institute of Engineering and Management, Kalyani University, Kolkata. He is having post PhD research experience in various institutes like University of France, Indian Statistical Institute, Kolkata. He has also served as assistant professor in Indian Institute of Technology, Roorkee, and now he is serving as associate professor in IIT Roorkee itself. He has also industrial experience, vast industrial experience. He has served as chief engineer in Samsung Research Institute, Noida. He was a research intern at HP Spain. He was also assistant system engineer in Tata Consultancy Services at Kolkata. His research area includes pattern recognition, computer vision, biosignal analysis, machine learning, and deep learning. Now I request the speaker, Dr. Roy, to kindly share his valuable experiences. Dr. Roy.
Yes, good morning, Dr. Sandeep.
Good morning, sir. Good
Good
morning.
morning. Good morning.
Good morning. So yeah, just a minute. Is my screen visible?
Yes, sir. Yes, sir.
Okay, perfect. Thank you. Yeah, first of all, I would like to thank Professor Kiran and Dr. Sandeep for inviting me in this event. Thank you very much. And thanks to the Institute G and DEC Ludhiana uh, for these invitations. I am really honored, and I'm very happy to share my experience with you. Okay, so today I'm going to present. Actually, I am having two sessions. I'm having two sessions. First one is on uh, recent trends in deep learning, deep neural network, and the second session we'll be discussing about this brain-computer interface. Okay, so yeah, you can actually talk to me if whenever you have doubts. You can raise your voice, and otherwise you can interrupt me. You can write your chat also, comments also in the chat box later. Once my talk ends, then I can take your questions one by one. Okay, so let's see this. Let's start this session with this deep learning network and its application, recent applications. Okay, so some details of my uh, profile. Actually, I am also associated with some journals as associate editor. Okay, I am there in this SCI journals as associate editors like IET Image Processing, IET Biometrics, IIC Transactions on Information Systems, Springer Nature Computer Science, and any other journals. Okay, so my team is working in pattern recognition, image processing, and machine learning. So pattern recognition, image processing, machine learning, it's short form PARIML. Okay, so the team's name is PARIML. So you may find details of my publication, projects, and team in this PARIML website, pariml.iitr.ac.in. Okay, you may always connect me at in my email ID partha@cs.iitr.ac.in. Right. Okay, so let's see this deep learning network. As you know, this deep learning is the latest machine learning algorithms. Okay, so which actually outperforms the traditional machine learning approaches, machine learning concepts. Okay, so if you might have heard about this autonomous vehicle driving. Okay, so you see this video. Is it audible, visible? There are some disturbance. If you have any comments, you can talk. Otherwise, you can actually please mute your mic. Okay, thank you. Yes. Okay, so you see this autonomous driving. It's now you might have heard in India there are many companies, industries, and government organizations. They are interested in this autonomous driving vehicles. Okay, there are several projects which work on this autonomous driving vehicles. So the concept is that this cars will move without any driver. So it started in 2019, okay, from US. Okay, this defense agency, DARPA, they launched these competitions of this autonomous driving. So the idea is you have the camera in front of the car, and this actually records all the scenario outside the vehicles, and then it understands. Okay, so now, yeah, 10 years back, those problems were actually little, though the problem is same, but the approaches were different. The approaches were mostly based on this traditional machine learning algorithms, like you extract some features from scene images. Okay, so you record record the video. In video, you have the frames, or you can consider the temporal informations like optical flow. And then from those images of optical flow, you extract the features like histogram of oriented gradients, shift, scale invariant feature transform, this kind of features, and then you apply in some algorithms like support vector machines, random forest. Okay, so you see that here the idea is they have to detect the objects. Okay, they have to recognize the objects, they have to detect some objects if it is there. Okay, so for example, they have to find where is the signal. Okay, so for example, if it is a red signal, then it has to stop. So it has to detect this kind of signals. Then also it has to detect if there are some objects like human being, animals, cars in front of the car. So they have to stop. Now you see, this should not work only in a daytime. Okay, so it should be illumination invariant. That means it will work in a daytime, nighttime. Okay, in different scenarios. Okay, so this is actually very challenging. Okay, so that's why, though there are some products available in Western countries, okay, in US, but in India, it's actually very difficult. Okay, so in in US, I found that one company, there are several companies. One was there, for example, pizza delivery. If you just order pizza and online, then automatically the car will come with a pizza, okay, without any driver, and it will actually deliver. Okay, so something like this. So there are several products which actually work without any driver, and these are actually functioning. In India, it's difficult because of the different scenario. Okay, so the rules are actually different, and they are not so strict. Some of the reasons are this. So now, if we just go to this, go to details, okay, how actually these systems work, okay, in this autonomous driving or this deep learning network. So you know this this deep neural network is actually the evolution of this neural network. Okay, so neural network, first you have this perceptron, and then perceptron is actually devised to classify two classes. Okay, samples of two classes, either for yes or no, positive or negative. Okay, it can only have a separator, linear separator hyperplane. Okay, linear hyperplane, which can divide the samples between two classes. Now, if the problem space, if the data space is more complicated, then this single perceptron will not be able to handle. So you need multiple layers, okay, hidden layers. So there actually you have this multi-layer perceptrons. Okay, so here you can bring here two hidden layers, three hidden layers, and then finally one output layer. So which actually which are all connected. Okay, so you see this all actually this connected hidden layers. Each neuron is connected to the previous all the neurons. Okay, so like that this works. So that's basically this neural network. Okay, now compared to this, you have this convolution neural network, where in this convolution neural network you have this hidden layers, okay, which actually something is happening. So there are some, I don't know. Okay, so you have this and this convolution neural network. You, instead of this hidden layer, these are actually some convolution layers. Okay, so there are some convolutions kernels. For example, it could be some edge detections, line detections, curve detections. Okay, and then they convolve with this full image, and then they find some features, and then these features are again convolved again in the second layers, and then they find more and more higher level features, and finally they classify. Okay, so in short, if you see this in a simple image, a simple RGB image, if I just give a image, so this height and width is the image height and width, and the number of channel is 3. And then if you apply, for example, 3 cross 3 kernels or 5 cross 5 kernels, and accordingly the intermediate layers size will be different, right? So this depth and width, height will be different. So what happened? So this lines, what is this? I don't know where these lines come from. Anyway, so there are some lines, actually these are, I don't know from where this line came from. Okay, so you have this this convolution neural network that we explained. So with this convolution neural network, you have actually some other blocks like this max pooling, and then activation functions. Okay, so if you see that if I have an image, simple image, okay, if I have a simple image and I am applying these convolutions like 3 cross 3, 5 cross 5 something, okay, so that's actually, these are the weight function, this will be learned. And then we have some activation functions like rectified linear unit, or for example, you can also apply some other activation functions like sigmoid, tanh. So there are many activation functions. And then you have some pooling, max pooling. Okay, so these actually applied in a blocks. Okay, so for example, convolution ReLU, convolution ReLU, then pooling, convolution ReLU, convolution ReLU, pooling. So this is very simple. So you are actually having these kinds of blocks one after another, and then you make the neural network deep. Okay, it's not a single one or two layers. Okay, it could be multiple 100 or 200 layers. And then finally, whatever features actually you receive, so this actually you straight, flat. Okay, so for example, if it's a 10 cross 10, okay, so you just make it a 10 cross 10, 100 features, and then 100 features actually you can apply here, input layer, and that's the final layer output. So output will be, it will tell you this is basically fully connected. Fully connected means all are connected, like in this neural network, shallow neural network. And then finally you go for object recognition, whether it's a car or airplane, ship or horse, whatever, right? So whatever, whichever is having more probability, the object will be recognized in that class, right? So that we know these things. And then you have actually many different architectures of deep learning. So for example, you have this AlexNet, you have this GoogleNet, you have ResNet, several architectures. So for example, if we consider these MNIST data sets, okay, MNIST data sets, like MNIST data set is for handwritten digit recognition. Okay, you have some digits 1, 2, 3 of 10 class problems, and then you want to classify those images into one of the class. So long back, it actually this LeNet 5 actually it was developed for recognition of these digits, English digits. So you see that it's actually they are applying this input first. This is the image 28 by means this image is actually it is normalized to 28 by 28, only one channel, that is a grayscale image, that is one channel. And then you are applying some kernels. Okay, so it could be some filters. Okay, so 3 cross 3 or 5 cross 5 some filters, and then If you are having 32 filters, so you will have the next layer will be 28 cross 28 plus 32. And then you make some pooling. So you reduce it and then filter, pooling, filter, and then you have this flattening features. You will have 1024 features. You can apply some dropouts and then you can get the final class level, okay, with the probability. Okay, that's basically LeNet 5, and similarly there are several other architectures like that I was telling, BGGNet, GoogleNet, ResNet. So these work on the different combinations of these convolutions, max pooling, and this activation functions. Okay, how actually you are connecting these layers one after another. So there are actually this the different architectures and many more. Okay, every day you will see that 7 different architectures are coming for these classifications. Okay. No, you know this VGG, ResNet, all this actually coming. So if you see this, if you have there are several, okay, several architectures are there. So if I just consider this one data set, CIFAR data set, okay, so CIFAR data set is for example, some object plus classifications. Okay, object classifications, you have these objects are actually size, resize into 32 by 32. These are all color images. That means 3 channels. And there are 10 classes of objects. Okay, airplane, automobiles, birds, cat. Okay, so like this, you have this different 10 class. And then each class you are having this 6,000 images per class, 5,000 for training and 1,000 for testing. Now this is a data set available online. So if you are interested, you can actually run your architectures with the different combinations of these architectures, and you see that which architecture is better. Okay, so if you just compare with this existing architectures, you have this VGG, ResNet. VGG is becoming 92.64, ResNet 93.02, and recently you have this DPR 90 to 95.16 and pre-act ResNet 95. Okay, so these are actually 95, 95, 96. Maybe nowadays there will be some more better architecture which can reach 96 or 97. Okay, but in AIMLDS datasets, the accuracy is almost 100%, only 99.7 or 99.8 maybe. Okay, so there are actually many datasets. Now there is also ImageNet datasets. There are many other datasets which are actually benchmark, which are called benchmark datasets. If you develop some architectures like this, combinations, permutation combinations of this max pooling, convolutions, and this activations. So you have to check that which provides the better accuracy. Okay, so then you can get a better publication, good publication. Okay. Now let's see that this is actually whatever we say talk. These are all about classifications. Okay, given an image, single image, you have to say whether this object is there or not in that image. So for example, if it is in this image, it's a airplane is there or not. Okay, this image contains airplane or not. Now this next problem is object detection. And object detection is it's a little different than classification. Image classification, that I'm saying that given an image, I'll just say whether it is image is having boat or it is having person. Okay, so this is actually, if you say that boat is there, so that means it will be classified as boat, it will be classified as person as well, because these both objects are available. I do not consider here that where these objects, okay, appear in this image. Now in object detection, this is the next challenge, that where this object appears. Okay, object recognition plus detections. There you have, for example, it is the boat, and this is actually you have to make bounding box. It's a very simple one, but otherwise this bounding box also could be different. Means you can make the bounding box rotated, okay, and then you can also make it very tight. Okay, so you can just make this based on the ages. Okay, how actually you can make the detector better. So let's consider a simple problem that how actually you can detect the objects. So you have these boards and persons. So where these boards appear, so board is appearing this, you just make a mark with a window, okay, where this board appears. Then persons, where these persons appear. Okay, so this is the object detection. How actually this will work? Then this object recognitions. So before that, you see this the actually latest some results. Okay, at present, how people can detect these objects. Okay, so given any image, you see these cards, so people can detect those objects very precisely. It's not only simple bounding box. It is with the segmentation. Okay, this pixel based segmentation, where is exactly the person. Okay, where it's for example, if there are so many people are there, where each person appears. Okay, so that's actually present object detectors works like that. Not only that, okay, it will also tell you that understanding, okay, what it is doing. Okay, so for example, you can say that it's a person is kicking the ball. Okay, understanding. Okay, so this person is eating donuts. Okay, he is throwing a frisbee. He is reading a book. Okay, so understanding. So it's person is holding a book. That means he is reading. So some understanding. It's a more higher level abstractions. Okay, understanding. So riding horse, talking on the over the phone. Okay, so how this actually works? So let's say this segmentation problem, object segmentation. So say simpler object. I'm just going to this different scenario, several technologies. So if you are interested, you can go into details. So this detection is there are several architectures. Okay, several architectures in object detection in an image. So for example, given an image, I want to know that which objects appear. Okay, and where what is the class and where it appears. So one simple algorithm is YOLO. Okay, it is also very popular. It came in 2016. Okay, NCBPR. So what do? They actually divide the image into small grids. For example, I can divide the image into 5x5 or 9x9 each block. Okay, cells. And now from each box, I want to know that where exactly the bounding box, okay, of that class, predict a class and a box for every location on a grid. So for example, I am having this grid. For this grid, whatever which objects appear, and if the object appears, then what is the bounding box? Okay, based on each grid, I want to have a object. I want to have the object data. Okay, so it will actually give me for each grid, it will give me a object bounding box along with the classes. Okay, class confidence. For example, I am saying this is a this one grid I'm taking. So for this grid is actually a part of the cycle. So it will try to find out this which is the bounding box in the image, which part of this image actually contains cycle. Okay, and then apart from this bounding box, I will also say that what is the confidence. Okay, so here, so each cell is actually trained, okay, with a detector. So for every cell, the detector needs to predict the object class distribution. It will predict two information. One is bounding box, another is confidence, class confidence. Okay, either class confidence is its cycle or its dog, and second one is what is the bounding box. Okay, that means whether this corner, it is the top left or down right. Okay, which corner it is. So these corners actually, this for each grid this will find, and then based on the confidence of this all these regions and these object classes, it will finally tell you that okay, which objects appear. So this is also similar. Okay, so you are actually having this convolution layers, max pooling, and then you see that here what we are doing for 7x7 image. So you are actually finding the 7, you are dividing into 7x7. So for 7x7, actually you are making it in a, you are doing the convolutions. Okay, so when you will do the convolution, actually in it at some points it will view the more info details of the object. Okay, at some point, because it's actually in different scales, sometimes some kind of scaling information is also there. So it will find that in which object is appearing for this block. Okay, so 7x7, and then it is actually finding this more and more detailed informations, and then finally it is classifying. So there are actually many more object detectors like this. So for example, this YOLO that we said, the SSD, RCNN, region CNN, faster RCNN, mask RCNN. Okay, so this is actually, if you see, the best was mask RCNN. YOLO, the performance is good, but these are actually better. SSD is better than YOLO, RCNN, faster RCNN, and then the best is now mask RCNN. So there are actually many more, okay, architectures for object detections. Okay, so which actually works, given an image, you will be detecting those objects, and also you can tell that which class it belongs. Now, there is another category in this neural network classes. Okay, so that whatever we were talking about, these were all about convolution neural network. Okay, you have this input, and then you are applying the convolutions, and then you are finding the final object recognitions and the confidence level. But nowhere actually this is output is connected to the some input. Okay, so that means this actually will not help you for sequential information. For example, these are all image, a single shot. If given an image, I want to say that whether which image it is. But if I want to say, for example, that a video, okay, so where you have a video, you will not work in a video. Video will not be it will not be split into multiple frames, and you will be working in every frame. Okay, so here actually you can use the sequence information, what information you have received already in the previous frame. So can you use those context information, those informations in the previous frame, previous to previous frame, and then can you apply? Okay, so these actually comes in another class that is called recurrent neural network. Okay, so where actually you are working on time series data analysis, where output is also connected, means previous output of previous frame or previous data is also connected to the present node as an input. So one of the best example is, for example, machine translation. Okay, so for example, if I'm just writing in English, so you can actually translate into in Hindi. Okay, so how actually this is possible? So for example, I'm saying this je parle français, and then actually it will be converted into I speak English. Okay, so how actually it is working? So there are also, so for single word Joe, it's actually I, then parlay. So it's actually, it will take the information of this word along with the previous word. Okay, and then this will combine together in one vector information, and this vector will be decoded into this English. Okay, so this is called recurrent neural network. Okay, in this recurrent neural network, you can also have multiple layers. Okay, so like this convolution layers, you have this multiple layers. Here also you can have multiple layers of RNN. So in RNN also you have, for example, RNN, you have this LSTM, long short-term memory, bidirectional long short-term memory, GRU, gated recurrent unit. Okay, so these kinds of architectures are available, which actually works for sequential data processing. For example, this one of the best example is machine translation. There are other examples. For example, I want for speech recognition, voice recognitions. Okay, whatever I say, you actually want to recognize. Okay, for example, handwriting recognitions. All these different kinds of examples, applications, where the information at present is depending on the output of the previous frame as well. So what I said in this example, you see this actually. So for example, you have some input. Okay, so for example, it's economic growth has slowed down in recent years. Okay, it's English, and I want to convert into French. Okay, so what we do, we actually make a RNN. Okay, so RNN architectures, it could be multiple layers. Okay, bidirectional or stacked RNN. Okay, and then you convert them, all this information, to a vector, and this vector will be decoded again to a translations. Okay, and another script. Okay, so that's actually, if you can study, otherwise you can just know that, okay, what is available. Now this actually can be included with the CNN, okay, deep learning, and then make the task more and more interesting. For example, now I can find, okay, an image, okay, with respect to a sentence. For example, I am just not telling that, okay, in this image whether the dog is appearing or not. I will say that dog is running. Okay, so some sentence, I will give a sentence, and then you have to say, you have to find out those images where it is you see this dog is running. It's not dog is standing or sitting. Okay, so now actually you are mixing this continuous, this textual informations along with this image informations. So it could be, so for example, given a set of images, given a set of sentences with respect to image, you check that which sentence, which caption is the best. Okay, that's called image captioning. For example, I'm saying that you have this one image where the dog is running. You say that, okay, dog is running, dog is sitting, dog is sleeping. Okay, so there are different sentences. Which is the best sentence corresponding to the image? There could be sentence generation. Okay, sentence generation is, given an image, I will just give an image and it will produce the textual descriptions. So for example, I'm standing in front of Taj Mahal, so it will produce that what is the caption, what will be the caption. So I do not need to write anything. Similarly, you have this image retrieval. So I want to search that. I was saying that I just want to search this. I am people standing in a boat. Okay, so that will not extract only the images of boat. It will find the images corresponding the textual. It will understand the textual meaning, and then it will find then image sentence corresponding. Okay, match images to sentence, and then question answering. Then you can also ask that whether in this image this is appearing or not. For example, I can say I will explain. Okay, I'll show you some examples. Okay, so let's see this adding captions. So for example, you have this image. Okay, and these are the sentence. So a cow is standing in the field. This is close up of a brown cow. There is a brown cow with long hair and two horns. There are two trees and a cloud in the background of a field with a large cow in it. Okay, so that actually it's a more detail. Okay, you see this actually you can add more and more detailed captions. Okay, so you guys, how actually, so you are given, for example, you can have a sentence. So from sentence to image, you are actually making a matching. It's not a single word based matching. That way, I'm just classifying, I'm just finding a cow or a field. I'm just saying that, okay, what it is doing, details. So, for example, this image captioning, more examples. A woman is throwing a frisbee in the park. A dog is standing on a hardwood floor. Okay. So you see, this still it is not visible, but we can actually find an image. So where is dog is standing on a hardwood floor. A stop sign is on a road with a mountain in the background. So you are actually give more and more details of the image. A group of people sitting on a boat in the water. Okay, so like that, you see there are several examples. Now here, given what it is doing, so you have, for example, you have a sentence, and then for each sentence, it is trying to find out the correspondence locations. Okay, so that is also, for example, from images. Okay, so you find out the different parts, segments, and then for each part, you try to find out which word of the sentence actually best match, and then you try to make the best matching of this image and the sentence with the minimum distance or minimum loss. Okay, so for example, you can say that dog plays catch with white ball near wooden fence. Okay, man playing among in a public area. Okay, something. So here also you have several data sets. If you are interested, you can see that, for example, data sets of images and sentences. So you have to basically, given some image, you have to match. Okay, so for example, Flickr 8,000 data sets. Okay, you have each annotated image is of with 5 sentences, 1,000 for validations and testings. Okay, then Flickr 30,000 images, 30,000 images, 1,000 validation, 1,000 testing. MS Coco datasets, 1,23,000 images, 5,000 validations, testing. Okay, so these datasets are actually you have to test. Okay, so if you approach some algorithms, if you develop some algorithms, you have to test these datasets to show that your methods robustness. So for example, given this image, it is saying that a tabby cat is leaning on a wooden table. So similarly, you can also work for video. So video is not a single man, is also shooting a car. Okay, so that's actually, you can find these different frames. In each frames or set of blocks, you find out some objects, and then for a set of blocks, for example, 10 to 15 blocks, you find an event. Okay, so you finding or describing the event in a block, in a video. Okay, so that's basically video captioning. Then I was talking that what about questions? Can I ask some questions like, for example, given an image, I can say that what are sitting in the basket on a bicycle? What are the things sitting? What are the objects sitting in the basket on a bicycle? So if this is my questions, and can you answer? Okay, so this is the question. So now it seems a little complicated, but if you check the questions carefully, it's actually not so difficult. Because in the questions itself, you get some hints. Like what are sitting in the basket and bicycle means you have some basket, you have bicycle. So you have to find out what is basket and bicycle. You have to find out the bicycle, you have to find out the basket, and then from those, you find that which actually is sitting. And then you get the information that it's dogs or cats. Okay, like that, there are actually different question answerings are possible. Okay, so it's that I was telling, that's a little recap that what we did, what we have discussed. You have some image classifications, then you have segmentation also. There are different architectures, YOLO, then you have this RCNN, mask RCNN, several architectures which actually tell you that in this image which objects appear and where they appear. And then along with this, actually you can combine this object and segmentations with the textual informations. Okay, so for example, now if I'm just saying that I have posted a photo of my photo in Facebook. Okay, so for example, a photo of I am standing with my friend and I'm in a hotel eating some foods. So you can say that, okay, so Partha is having lunch with Rahim in restaurants on this day, and they are happy. So like this, actually, you can generate the full sentence. I do not need to write anything. Okay, and then later, if I want to search in these images, a set of images, that okay, where Partha appears in these images. Okay, can you find some images where Partha is having dinner? Can you find some images where Partha looks happy? Okay, so these actually you ask some questions and you want to find. Okay, so that's basically you are making a correspondence with this images along with the textual description. So textual descriptions, you are actually using this recurrent neural network. Okay, so there recurrent neural network, for each words you are having some correspondence image. Okay, and then you try to match this words to image, and then you find out the meaning. Now, in our lab, research lab of Parimals, we are also working in different problems. So some of these problems are handwriting recognitions, the gesture recognitions, and then action recognitions, and brain computer interface. Okay, so if I just explain this handwritten OCR, okay, so you know this OCR seems a little easy, but it's not so. Okay, so for example, I was talking about this AIMLDS data sets. Okay, so AIMLDS data set, you see this top left corner, these are the different digits. Okay, it's a 10 class problem, and then you have to classify. Okay, now if you see this, it's a very simple problem where you have only a single image appearing in an image and you are classifying. Now if I move to a little more complicated, okay, so that means you have actually not only going for the single digits or character. Can you recognize the word foreign, guest, president? Okay, you see this writing style. Okay, so how they are connected, it's not only about a single character. You have basically where you have these characters are not separated. So separation is actually, when it is separated, it's just simple recognitions. But you have to go, for example, it's a identity detection also, whether this character appears or not. Now the problem is whether which is the word. This problem can be thought of in two different ways. Either you can go with this full word recognitions, like whether which word is having foreign. Okay, so this is foreign, these are not foreign. Okay, so it's a holistic whole image you consider as an object. And second approach is you are actually going with a sequential, okay, or analytical approach, where actually you consider that, okay, I will just analyze like human brain, that okay, so what is appearing. It looks like O, then L, and then R. Okay, something like that. Then you say that okay, it's already OL. But later you see that okay, it is not. It will not be AOL. It will be AL. Okay, so that's basically word-based recognition. That's the analytical approach. Okay, so that's a little complicated than the previous one. And then if you go to this next higher level, so it's a given. I will just give you a snapshot or image of my handwriting, and then can you write the full text? What is it? What is written over there? So, for example, imagine so I don't know, vast sheet of paper on which something straight lines. Okay, so you have a full text and you have to recognize. So it is not just a recognition of each word, but also you have to understand the full meaning. Okay, so for example, some words may not be correct, but if you have to recognize the full sentence properly. Okay, that is in English, if you consider. Okay, this is the complexity. Now, if you come to Indian context, okay, Indian context, what will happen? If you see this in India, corresponding where is in English, you have only this 10 digits and 52 alphabets. In India, you have in Hindi or any scripts, you have many characters. Okay, so number of classes are huge. So when you go from this English to Hindi, so the number of classes are a lot. Then this is actually more challenging. And then if you go for this word, okay, in word actually it is these characters are connected along with some modifiers. Okay, so for example, you have this half consonants, modifiers, which are all connected, and then can you recognize these words? And then you can have some full sentence. And now, interesting thing is that when we write this kind of sentence or paragraph, sometimes we have 2 or 3 languages. So okay, so for example, I am writing in for example, I am from Bengal. I can write in 3 languages: Bengali, Hindi, or English. 3 languages I can write. Okay, in a single page. So you have to then have to recognize all these 3 scripts along with this recognitions and with the meaning. So that's actually more complex. So now if I'm just going to a more realistic, okay, so I was there in Tirunelveli in Tamil Nadu. I saw this scripts, okay, so because I'm not from that state, so I didn't understand. So similarly, many of us will not understand this one. Now, can we develop something with this deep learning framework which can take this kind of images or videos and can translate? Okay, so that should be a good applications. Okay, it will be really handy. But if you consider in India, OCR state of that, it's actually not so rich. Okay, though we started very late, 98, 2000, which actually work on this printed character recognitions or word recognition, but still there are so much problems. So I just showing one a document here, which actually you see these characters are written in different orientations, different size, okay, different complexity. For example, there are some complexities like document image will also some problems. Okay, these are different problems that this because of this aging effect is there, and then sometimes the backside information can come up. Okay, and actually it may be difficult. So yes, deep learning can help you. Okay, so deep learning can help you, and it actually shows good results. So what is the architecture? So here actually you people are doing combining this convolution neural network and RNN. Convolution neural network for extracting features, RNN because it's a sequential. Why sequential? because the text is not of a fixed length. Okay, I am saying that, for example, this image, this is it could be precedent, it could be post, it could be sometimes the text will be of 3 letters, sometimes the letter will be of that word will be of 10 letters. Okay, so that's why that width is not fixed, height is fixed. So that's why you can use those features in a temporal sequence. This is a this analytical approach that I was saying this. Okay, I will just go from left to right in one character at a time, and then I'll see that which is the best combination of characters appear in that word. So for example, given a word state, okay, so something like this printed text, so I'll just extract some features like convolution, max pooling, convolution, max pooling, and then I am having some features, okay, feature sequence, and then for each column I'm just making it I am applying in a RNN or LSTM. Okay, so this actually you can feed this each column as a feature. Okay, this is the deep learning features, the convolution neural network features, and this is applied in RNN. It could be also stacked LSTM. Okay, so multiple LSTM RNN could be there, and then you can finally apply some transcription CTC layer for this decoding. Okay, what is written over there. So that's the word recognition, handwritten word recognition or text recognition. Okay, so for example, this actually you can bring it, for example, this. So for example, if I take a photo, okay, so I just want to know that where this text, where the text appears and what is the meaning. So similarly to the object recognitions, I am just focusing on text. So what is the text and where this text appears. Okay, so it is actually similar to object recognition, but little complex, because here the text is there are several variations. Okay, so it could be you see this actually is a straight line. Okay, but it could be for example, you can see this a pillar can also appear as a straight line. So every pillar will not be a text. Okay, so that's why this text detection recognition is a little complicated. So there are many focused area, okay, on this text recognitions. And considering this this framework of this CNN RNN combination, there are also some frameworks in Indian script recognitions. Okay, so Indian script recognitions also we have several frameworks which will recognize your word. Okay, so given a word image, what is the what are the ASCII text. Okay, but there is no system I have found till now which actually can translate your full sentence or full paragraph. So can you develop something which is actually text, which takes input as a handwritten image and translates what is written over there? Okay, so there is also work which actually, for example, this text generation. Text generation is, for example, this is a okay, so I'm just giving an example. As you know, this now with deep learning, people are actually generating, okay, lots of fake images. Okay, fake images, like for example, just few months back or 1 year back, you might have experienced in Facebook that people were posting their profile pictures as if they look like 70 years old or 60 years old look. Okay, 60 years old look like. So these are actually fake images, but which look realistic. So similarly, given a text line, so can machine also write similar way? Okay, so machine also can write. So if you see this, these are text, and these texts are generated by machines. Okay, so if I do not tell you that which is real and which is generated, then actually it will be difficult. but still it's a little, it was long back. Okay, you see this 2013-14, but after that there are several good framework is there actually, which produce very realistic synthetic images, okay, using this deep learning. Now I move to another platform, that is a sign language recognitions. Okay, sign language recognitions also we have been working, because in IIT Roorkee we have this speech and hearing impaired institute called Anushruti. So there are many students are there. So if you want to communicate with the speech and hearing impaired people, so actually it will be difficult, because they use their own languages of this gesture, and we have our voice. Okay, so but if we want to communicate among each other, because the languages are different, we need some interface for translation. Okay, so how actually you can use. So for example, I'm just telling one, I'm just showing one video what we have developed in IIT Roorkee. Is, for example, you have one device, it's actually a lip motion device. Here it's a small device which will actually captures your arm and fingers. Okay, how actually this move. So you see in the right side of the monitor, there's a the movements of these fingers. Okay, so those movements, it's actually when someone is making a gesture, so we consider these movements, and then we apply this recurrent neural network, LSTM, these kinds of architecture for recognitions. Okay, what he is saying. So for example, he is making a sentence like bad, flower, okay, or stand, something. So this actually will say that, okay, it's, for example, it could be a flower, okay, or morning. Okay, so here it's morning. So it's not only a single word, it could be a full expression. For example, he is saying that I'm going to school, how are you? So if he says a full expression, so can you translate that expression to this ASCII text? Okay, so that's actually this from one language to another language you are translating. Okay, so that is this we are working, and here we have this we are using this recurrent neural network deep learning framework. Okay, so now here also you have several complexity. Okay, so I sign language recognitions. So what we are using is basically we are using a sensor based approach. Sensor based approach means sensor should be there which actually captures the movements. But when you want to work with this simple camera, RGB camera, there are several data sets. Okay, so for example, the simple work is given an image, can you classify what is that? Okay, what is this character? Similarly to this character recognitions, you have this PAP123 something. Okay, this is a sampler. Now, if I'm just going to the next level, that is a word level recognition. For example, this lady, she is saying pizza. It's a full gesture. This guy, he is also saying a yeah, you have seen this guy, he's making a pizza. Okay, so this pizza and this pizza, these are actually different. Okay, so this is a complexity. So given a same word, their gesture could be different. But can you have, if you see this, you have this video input, and can you classify it as the which gesture it means. Okay, now if I'm going to the next level, okay, so for example, next level is, you see that he is saying, okay, so a full expression. Okay, so that actually it is more interesting. So what we have to, I have shown you in the previous example, that's a full expression level. It was a simple gesture level, but it was only with the sensor based. Okay, it only works with the trajectories, not a camera based. But here we have also a system which works on sensor based, but it also works on continuous. And so if he's saying a full sentence, we take the full trajectory movements and we can classify, or we can generate the sentence. But if you have this video based input, so whatever expression he is saying, can you do that? So there also you can have this CNN based feature and then RNN based recognition translation. Okay, CNN, RNN both actually, if you have to combine them together. Okay, so in this type of platform, and then only you can go for a better good results. Now, next, we are also working on this activity understanding. Activity understanding is, for example, you have also different problems. Activity like what action I'm doing. Action. Okay, so I told you this video event recognitions, right? And object recognition. So, for example, this guy is only doing some exercise. Okay, it's a very simple. So there are several data sets out there which actually does this exercise. Then you have this kind of exercise. You have this exercise where there are multiple persons, 2 or 3 people will be there who are actually doing activity together. They could be fighting, they could be friendly. Okay, so they could be working together. Then there is a more challenging is, for example, there is a group of people. Okay, so 5 or 6 people, they are doing some activity. It's a single class. That's also single class problem. They are doing something. Okay. Now, our lab, we didn't work on this camera based in information, but we were working on this mostly on the sensor based. Okay, that in like sign language, we use this lip motion sensors for acquiring the input. Okay, we didn't work on the camera. Similarly, in a human also, for example, if I have a camera in a room, I am not working with this RGB camera. We work with this Kinect camera, Microsoft Kinect, which actually, if you record, it will generate the skeleton informations, like where is the head, where is the leg, and means it's a stick diagrams of the skeleton. But now there are actually several architectures are there in computer vision community, which if you give an input of a video, it will generate similar kind of stick diagrams. Okay. So for example, with these stick diagrams, you can also do the same thing that, for example, someone is standing, sitting, walking. So if a person is doing multiple activities, for example, I am doing first I was standing, then sitting down, I was drinking water, and then I did some exercise. So given some activities in a sequential order, so can you tell me that what this person did? Okay, so whether this guy was standing or he was sitting, and in which frame, for what durations. Okay, so this is basically the segmentations or detections in this full video. I want to mark where exactly this person was talking over phone, or how long he was doing exercise. Okay, so this kind of activity. So similarly, human interaction that I was saying, that 2 person or 3 persons, if they can work also together. So for example, 2 persons, they're fighting, or they could be friendly behavior. Okay, so that's basically some interactions. If there are multiple interactions among people, then what interactions they are doing, whether they are fighting or they were talking friendly. So there also you could use this CNN-RNN. Okay, CNN-RNN also could be there together to know that. So for example, here we did with the stick diagrams, when we have this junction points movements, we apply this LSTM, deep LSTM framework to know that what activity they did together. Okay, so that's another one, but I do not. I just want to skip. This one is more interesting. That's actually more complicated, and this is actually more realistic scenario. Okay, this is a little more complicated, where you have many people, and they are doing activities. Okay, and then the idea is you have to make an alarm if there is some suspicious activities. Okay, so for every person, you have to know what he is doing. If he's standing, sitting, he's eating, he's running, or what. And then you have to know that if there is a suspicious activities, like if they fight together, or if they leave some bags and then they move. So you have to make an alarm. Okay, so these are actually video surveillance. It could be in indoor, could be in outdoor. Outdoor, it could be also like this similar activity, or you can also make some traffic analysis. For example, many cars are coming here and there. You have to check that, okay, which cars you will allow first. Okay, so there are other works like colorizations of images. For example, if you give some input images, color black and white. So for example, we have this 50 years back, we had this black and white videos. Can you do a remake of this black and white videos so that it actually looks realistic? Okay, so it's similar to this deep it is these are all deep learning based, but there is actually you have some synthesizing. Okay, synthesizing means you are generating machine is generating just color images so that it looks realistic. So for example, this is the real image, and I have made the color. Okay, with this for example, this is the color from machine which look realistic. So for example, these are the image, gray, black and white gray images, and then we make this color. So here we have used some this convolution architectures only, but encoder decoder types. So first we use this encoder with these convolutions. We have some we encode into a vector, and then this vector is actually next decoded into this color image. Okay, that's actually generated, and there is another architecture which actually says that whether this image looks realistic or not. Okay, so I just do not want to go more. So these are actually some more papers are available. Okay, for synthesizing video surveillance, sign language recognitions, handwriting recognitions. So you can find them in all these papers in this parimol.iit.ac.in. Parimal website, all the papers are available. Some data sets are also available, so you can just download. You can work on these problems. So let's consider some of these comments if you have. Okay, so and then we can start discussing, because there are several things actually. There are deep this CNN RNN combination, actually it's a huge lot of things are there. Okay, so there is no end. So every day there are so many things are coming. Okay, so can we replace FC layer with global average pooling? So if so, what is the advantage of using gap? Okay, so mostly people what I have seen. Okay, so this you have you are saying this with you want to replace this fully connected layers with this gap. Okay, so most people they use this fully connected layer at the end, and this you can also apply global average, but I am not so confident with these questions, because now you have to do this experimental study. Okay, so according to applications it varies. So in some applications, you will see this FC layer is good. In some applications, this other information. So that's actually this. I was telling them these are actually different permutation combinations. there are many pieces, elements are there. So these are like some toys games. Okay, so you have to just plug and play. Which combination actually gives you the best results in some applications, and then you see you just publish. Okay, so this is the best framework, end-to-end framework for these applications. Okay, so given this data set, this is the end-to-end framework for this application. Semantic segmentations, pixel wise normal segmentation. Yes. See, segmentations, yes, that I was telling, segmentation could be of various kinds. Segmentations, you can say that you can make a bounding box, okay, rectangular bounding box, and that is actually tells you that, okay, this is the image detector. But when you say that, okay, pixel wise segmentation is actually difficult, okay, pixel wise, so every pixel either it will be it will lie in the object, otherwise no. So that's a pixel wise checking you have to do. So there are actually several performance measures based on this IUC, okay, this intersection of union over this overlapping. Yeah, IUC or IOU, I don't remember this full form. It's basically you have this whatever you are detecting, IOU, okay, intersection of the objects and given whatever is the ground truth. So you are basically finding, given this bounding box, whatever where you are locating the objects, and you want to know what is the precision, how many pixels you are detecting correctly, how many pixels you are wrongly detected. Okay, so there actually you have to find this precision, recall, F measure, ROC curves, all these actually there are several metrics are there. So you have to compare with those things and see that which is actually best. Semantic segmentation is different. Semantic segmentation is, for example, you have to have this. Say you have some logical information. Okay, so for example, this word to word, if you just say that. So sentence, you have a given sentence and you have an image. So which words appear where? Okay, that's basically what to segments. You are detecting these objects, words, okay, given in the textual informative sentence, and you are finding it in the image. Okay, and then you want to find the relationship. Okay, so semantic. For example, if I am saying this, I am this one guy is reading a book. Okay, so reading a book. So you have to find this person and book, and then you are making a relationship. That's actually semantic segmentation. Augmented virtual reality. Yeah, there you have actually this augmented virtual reality. We have several augmented virtual reality applications from this gesture recognitions, from this text object detections recognition, because this actually when you go for this augmented AR VR, augmented reality, virtual reality, or mixed reality, so you have to understand that you have, when you wear the device, you have to understand that where exactly this object appears. Okay, so and then you recognize and then you overlap, okay, with some you are rendering some other objects. Okay, so that means you are recognizing, detecting, segmenting, and then you are rendering. So that's actually when you go for this augmented reality, then it comes. But virtual reality is totally, it's a different. We are just immersed in some scenario where maybe it appears in the reality or not. Virtual reality is totally different. Okay, so maybe it may not be existing. You will just imagine whatever is there. Okay, but in augmented reality or near virtual reality, there actually you have to detect those objects in the scene images or video, and then you have to render. Detection for 3D images, of course, yes, 3D image is also there. Okay, so this whatever we have explained, this CNN, it's not only for 2D. Okay, so you can go for 3D. So when you go for 3D, initial 3D is, for example, I am just saying this, the first image, the input is of 2D height and width and of 3 channels, red, green, blue. So you can consider that it's also of 3D. Here the depth is of 3 channels. Instead of 3 channels, you can consider that's also another 10 channel information is there, or another depth is there. So you can extract the features. You can have a kernels of whatever 5 cross 5 cross 5 or something, and then you extract those features, and then you have multiple features, hidden layers, and then you can apply. Okay. So that's this deep learning of these different architectures. Yes, anything else? Yeah, any doubts you want me to clarify, we can discuss. See, I didn't discuss about this this another architecture that is called GAN, generalized generative adversarial network, that is actually used for this generating synthetic images. Okay, so this from color grayscale to color images, these actually are used for using this GAN framework. This is the advanced framework of this deep learning. Okay, so if that is fine, then we can move and then we can meet again in 15 minutes, right? With this brain computing interface. If you have some doubts, then we can still clarify. We have time, 5 minutes time.
Participants, if you have any question, you can ask now. So, sir, I think there's no more question. So,
Yes.
thanks, thanks, Dr. Partha, for such an informative session. So, participant will meet again at 11:15. Sir, we'll have break at till 11:15.
Yes.
Okay, sir. We'll meet again at 11:15.
Sure, sure. Okay, thank you. Yes.
Thank you, sir. Thank you.
Hello.
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 Yes. Is it audible? Is it audible?
Yes, sir, you are audible.
Okay, fine. Thank you.
Hello, good morning, sir.
Yes, good morning.
Welcome back, sir.
Yes, thank you. Thank you.
Shall we start?
Yes, I am ready.
Okay, sir. You may start the session. Then I think participants are joining. Around 57 participants have joined. If you want to wait for 5 minutes, then it is okay. Otherwise, you can start.
We can wait for a few minutes, 2-3 minutes. We can wait and
Okay,
then we'll
sir.
start. So you are Dr. Kiran Jyoti, right?
Yes, 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 sir.
Okay, so I I didn't know. So everything is virtual, right? So we do not know.
This is a new experience. COVID has given us new experience.
Yes. Yes. It's different, bad,
Yes.
good, everything.
How are the participants, sir?
Good. Yeah, there were some questions
Okay.
the last session. Hope it was useful.
Yes,
The
sir.
last session.
Yes, sir, it was. All the participants were connected all the time.
Great.
800. 800 क्या 800
Good, thank you.
Total gain or loss in whole transaction करना हम लोग टोटल सीपी टोटल
So you can start now. I think participants have joined.
Yes, ma'am, we can start.
at what rate percent and at what rate percent एक में हम
Okay, is my visible?
Yes, sir, it is visible.
Okay, thank you. So thanks all of you. So let's start the second session. So we have now this brain computing interface. Okay, so and some applications of this BCI. So if do you have any experience of working with this BCI earlier? Anyone worked? Okay, so it's actually, you might have seen in this hospitals, if some patients are having, for example, heart related disease, they go through this ECG. Okay, and then there are some records of this ECG, and then doctors analyze, checks those ECG signal in a paper and or in a monitor, and then they find out what is the pattern. Based on the pattern of this ECG is one-dimensional. These are all one-dimensional signals. So in these signals, so this, if they find some patterns of some known disease, say they can diagnose. Okay, so they can detect and accordingly medication works. So they can know that what is the disease classification and also severity. Means whether it is of high severity or low severity. Okay, so this is of ECG, where you actually, these patients go through this ECG process. Okay, so there are some electrodes, they record the data of heart. Similar to this ECG, there is another kind that is called EEG, electroencephalogram. Okay, this also records data from, but not from here heart, but from brain. Okay, so brain related data. So the patients wear some wearable device where you have these different electrodes which are connected, and then these actually record the informations of the on neurons. Neurons means actually this is basically in, as you know, in brain there are actually billions of neurons are there. Okay, so according to our activity, okay, so it could be, for example, if I'm walking or listening music, so then the neurons of on the brain, they will do they will transfer some information. Okay, pass this information. So when they are actually doing this message passing, so there are some changes in the potential. Okay, voltage difference could be recorded from over the top of the skull. So these are actually recorded. These are in microvolt range. So it was first recorded in 1929. There are some alternative devices which actually also works to diagnose this brain-related disease. So, for example, this fMRI, MEG. But these actually works on image. Okay, so 3D data or multispectral data. Okay, so where you have a huge volumes of data, and then there are some image processing also. People or doctors also, they analyze, they see that where is actually there is a gray part, white part, or this what is the tissue, means cancerous disease or not, or something. Okay, so based on this from this imaging, okay, so imaging data, these doctors analyze. These are alternative, but those devices are very heavy. These fMRI image devices, these are very heavy, large, and their maintenance cost is also huge. But contrary to this EEG device is very handy, and they are very cheap. Okay? And they produce also very good results. Okay, so in hospitals, in many hospitals nowadays, abroad, of course, in India as well. Now this AIMS or this top private hospitals, you might have seen these EEG devices where the patient's lying on the bed, and then there are some helmet type of this wearable sensors. There are so many electrodes are there connected on the scalp, and they record the signals of the patients. Okay, so this actually these records are analyzed for different brain related disease, like for example brain tumor, stroke, sleeping disorder, epilepsy, brain death. Okay, now depressions, this kind of analysis. There are actually many papers are also there, and now in many places they work from those ECG signals, EEG signals, okay, to know that what is the disease and the severity. There are also some other applications where researchers are uh, analyzing these EEG signals for different applications, not for uh, healthcare related. Okay, so beyond this healthcare related. So, for example, I want to know this emotion of the person. Okay, so whether some person is happy or sad. So, for example, I want to know that, okay, if I am watching some products, okay, so whether I'm really interested in the product or not, neuromarketing kind of thing. Security, for example, if I am if I just provide my data, EEG data, can someone analyze those EEG data and check that whether it's a genuine or not, similar to the Aadhaar. Okay, so it would be used as, for example, this you have this gesture, this interface, okay, computer interface, where, for example, if you just say that, okay, I want to move my car straight, okay, just the imagination. I'll not do any gesture movements, or I will not speak anything. I will just imagine, and accordingly the cars or objects will start movement. Okay, so you might have seen that, okay, in videos that, okay, so some of the drones or cars are moving according to some imagination of some person sitting in a chair. So this could be helpful also, for example, this for patients for controlling their wheelchair or mouse movements or other activities. So I will actually discuss today this how this details of this how you can acquire the data, okay, and then how you can use the machine learning technology for classifying these kinds of applications. Okay, some of these applications. So some devices, there are several kinds of devices. Okay, so this, for example, this some devices are coming with one electrode. Some devices can come with 2, 4, 8, 100, 200, 256, something. Okay, so lots of variations are there in the design. Okay, so actually it depends how you want to collect the data. If you want more dense data, lot of data, then you have to use a dense device. Well, that is actually a little costly. If you want to buy a simple single electrode, that cost around 6,000, 7,000 rupees, Indian rupees. If you want to go for 256, it will be more than 1.5 crore. Okay, so that's the variation, range of the price of these electrodes. And most of these devices are now non-invasive, means they do not require any surgery. You just wear on top of the skull and you record the data, and you can start doing the application. Either it could be healthcare related or it could be no others. Okay, like normal applications. There are also devices in BCI devices which are invasive. Means it used to be before, but that's actually more accurate. These are invasive, means where doctors, they do surgery, and then these electrodes are actually implanted in the within the brain. Okay, so the advantage is that it will actually, there will be no noise from outside. Okay, so you will get the data better. Okay, but in non-invasive devices, there are actually, you will get a lot of noise. So there you need some softwares, many different softwares for noise cancellations, which may reduce your actual signal. Okay, so I show you one video how to acquire the data. Okay, so you see, this is actually from our lab. This is a device of 160 electrodes. Okay, and this guy is actually putting some gels. Okay, it is not an injection, it's a gel which he moves the hairs and connects the electrode to the skull. Okay, the skin of the skull, so that it connects better. Okay, and there will be no noise when it connects perfectly. Then in the GUI, graphic user interface, you will see that these electrodes appear green. Otherwise, it will appear red. So if there are 32 electrodes, these 32 points you will be seeing, and for each point there will be some signals. Okay, so here this one point I just want to explain. So for each electrode, it will show the records. Okay, this potential difference of the neurons from that part of the brain. Okay, so there will be lots of neurons, so it will be accumulated voltage difference of that part in that electrodes. It will collect. Okay, and then it will show. So there will be change here of the signals. So you will get similar to this ECG, this one-dimensional signals. Now for every activity, there will be some change in the signals. Okay, so for example, this if this get see that when he is blinking, there are large uh, uh, peaks and valleys. Okay, and when he is not blinking, so there will be more like that for each activity. Okay, so your electrode will reflect. Okay. So now in this actually in the brain, as we have studied already in this from biology, you have in the brain there are different parts. Okay, frontal, parietal, occipital, temporal, cerebellum. Okay, and this different parts, and each part is actually uh, active. Okay, while you are doing some action. Okay, so for example, you are speaking, so some parts will be active. When you are listening music, some parts of the brain will be active. So if your electrode is in that place and you are recording that electrode, so for that activity you will be getting that signal. Okay, so for example, if you are if you want to analyze the reading behavior of a person, then you may place your electrodes in this parietal lobe, and then you may get the records of this electrode. So you will get the signal better, okay, than these other electrodes. All other electrodes will also show you some information because there are some connections, okay, but these electrodes will be giving you better informations. Now, the position of these electrodes over the device. So these actually are maintained in this 10-20 system, international system. So 10 and 20 refer to the fact that the actual distance between adjacent electrodes are either 10% or 20% of the total front to back or right to left distance. So in this skull, it is from left ear to right ear. So whatever distance you are having, so based on this, actually you collect 10% or 20% distance, okay, of for each electrode from these different electrodes. These are placed, and for every electrodes you collect the signals. That's actually the standard international process, international protocol for this electrode placement. Now, from each electrode that you have already seen, these are, for example, frontal F4, these are these different electrodes. You get these signals. Okay, so these signals will be in microvolt range, and if you are collecting for 2 minutes or 3 minutes, you will be getting signals like that. Okay, so in different parts, you will be getting this different. For each electrodes, you'll be getting this kind of signals. Okay, and then these electrodes are also named accordingly. So for example, F frontal parts electrodes will be named as F, which start with F. And you see that some kinds there you have this odd numbers. So odd numbers will be reflected in the left part, and this right numbers will be reflected in the even numbers will be reflected in the right part. So F4 is the basically in the right part, and F3 will be in the left part. Okay, so like this, actually these electrodes are numbered and their position, and you will be getting the signals from each of these electrodes. So they are put in these electrodes while you are the companies are designing. So there are some amplifier and noise removal cancellations technologies are there, so that the signals are better reflected. So when you record, when you see in your the recorded file, okay, in the text files, you will get, for example, this informations. Okay, that means this amplitude. Okay, so amplitude will be finding that, okay, for example, this first time, if I am having 14 electrodes, if I place 14 electrodes, so in first time frame I'll get 14 data, and then second time frame again I'll get 14 data. So for first I'm considering first one, if it's the first one is F4, so if I am having 500 time frame for, so F4 will be giving 500 data for each time frame. Okay, then similarly 14 electrodes will be giving me 14 columns. Okay, 14 signals. Okay, so for every time frame you will be getting these kinds of data. Now you see, if you see this EEG signals, so there are actually some patterns. Okay, so when someone is very active, okay, he is listening, playing music, or for example he is thinking something, so his signals will be showing lots of high frequent signals. Okay, when he's moving towards this non-active activity part, when he's not so active, then the signals will be showing less high frequency signals, and then it will have more on less lower frequency signals. Okay, so you see this excited, relaxed, slowly this high frequency components are getting reduced. So we can actually classify, these are all termed, okay, from this literature. When the signal shows this less than 4 hertz, okay, this signals frequency, that means this is a sleep stage, deep sleep. It's a 4 to 7 hertz, it's a theta, and then alpha, beta, and gamma. Okay, gamma is cognitive, okay, 20 to 60 hertz. So when you are having this higher frequency signals, it is active processing, relatively desynchronized active. Okay, so if you get some data, if for example I'm collecting a data from some patients, so I'll be collecting, so as I was saying that this these are all non-invasive, so you might receive several noise. Okay, and then so we need some softwares to remove these kinds of noise. So I can use some wavelet transform, Fourier transform, and then we find out what are the frequency components, and I can remove. And then I can also use some DWT transform, or this discrete wavelet or discrete Fourier transform to know that what are the frequency components. And based on these frequency components, we can split these signals into these different bands. Okay, so in each band, for the alpha, if you are having this alpha, only 8 to 13 hertz signals frequency components will be there. If it is a beta, only 14 to 20 hertz signals will be there. Okay, so like this, actually, if we see the signals, so given a raw signal, and if it is decomposed into alpha, beta, gamma, delta, theta, so I can find this different components, okay, band-wise signals, so which actually reflect this in that range. Okay, and now once we have these signals, for example, I am using gamma band signals, and from these signals, it's a raw signals, I find this gamma signals using this discrete wavelet transform, and this is the, so I can decompose. Okay, so I just find out that frequency signals, and I just you apply. Okay, I just make the signals. Then if I have these signals, I can see, for example, this in speech placid recognitions, or in signal recognition, signal processing, people use some feature extractions. Okay, so given a signals, I want to know that what is this signal meaning. Okay, so these signals, so if I am having, for example, I'm extracting from 14 electrodes, so 14 electrodes for each time frame, I will have some alpha signal, alpha, beta signal, gamma signal, something like this. Or I am having 14 electrodes. If I'm having 15 electrodes, 50 electrodes, I'll be having 50 alpha, beta, gamma, delta signals. Okay, And this, from those information signals, I can actually find some features like root mean square, standard deviations, energy mean, these kinds of features. You could use some other features as well. You could also devise some other features. These are a traditional approach. I will also go to the deep learning. Okay. So traditionally, these features could be extracted, simple features. If you are having 4 or 5 different signals, so you just make some simple mean, average, standard deviations, you can find some features. And then once you extract these features, you actually apply in a classifier. Classifier could be, for example, it could be support vector machine, neural network, random forest, hidden Markov models, deep learning. Okay. So, for example, I am having, I collected data of 40 time frames, okay, some signals, okay, from 14 electrodes. So, whatever information is there, so I'll be applying, I extract the features and then I use some classifiers. So, this is the machine learning paradigm, or okay. So where we are extracting, we acquire the data signal, we extract the features, and then we feed into some classifiers. So this paradigm could be used in healthcare or non-healthcare. Healthcare, for example, someone wants to work on epilepsy, okay, epileptic seizure prediction. As you know, I will not go into details of this healthcare related stuff, but the other one I will be talking more. So I'll just show you some 1 or 2 applications that if, as you know, this in India and worldwide, there are so many patients are there with this epilepsy. So it is a neurological disorder that occur in the brain and affect the nervous system. So actually, abnormal excessive hypersynchronous discharge of neurons appear in the brain, and that shows as the seizure. Okay, so if in this hospital they collect the signals and then they do this analysis, and you see this when in this epileptic seizure, there are basically, if it is a normal signal, pre-ictal signals and ictal signals. Okay, so these signals actually they will change their pattern. You see that I was saying this eyes open, eyes closed. So similarly, in every activity in this different parts of this seizure, so duration, this signal will change their rhythms. So based on the rhythms, so doctors, this machine learning could be actually used for classifying that this signal means pre-ictal or ictal, or it's a seizure or not. So you can actually have some confusion matrix of this. These are all available, these data sets. I'll go to at the end to show you that, okay, what data sets are available. Then you have some other works like deep learning. Okay, so deep learning framework also could be used, that I was telling that given some data signal, the last sessions we have discussed this recurrent neural network, right? RNN, LSTM, BLSTM, these are of this deep learning framework, which are used for sequential data. Sequential data means when you have this time series data analysis. So these EEG, ECG, speech, these are all time series data. So when you have time series data, you can actually use this LSTM, BLSTM framework. So you can extract some features that we have explained, and then you can also use some other features, and then later you can use some classifiers like LSTM, BLSTM. Okay, like one layer of LSTM, another layer of BLSTM, and you have some set of layers like this, and then finally you classify. Okay, there are actually several architectures are there in this deep learning paradigm, that given a signals, so how actually which architecture is better. So it depends also that according to the applications. Okay, that today that I was saying that I will be discussing more on the this other parts. That's what people are doing beyond the clinical purpose. So, for example, Here in this during this corona period, we see that we are all having this online classes. So as I do not see you all, okay, but if I am having some this, if you wear this device and I am having these softwares, I could actually understood from this device that what is your gender distributions or age distributions, whether you are really interested or not, in which slides you are interested, in which slides you got lost, okay, where you got boring, you are not interested at all. Okay, so this kind of information actually I could easily uh, check if I am having that software. Okay, so that's actually whatever you are thinking, whatever your mental status. Okay, so that could be reflected from your EEG data, and using that software I can see, understand. So that's actually this the different applications which are beyond this clinical purpose. So some of these applications I will discuss now. So for example, this is one of this is age and gender recognitions. So given some EEG data, so for example, I'm collecting some data from some persons. So can I tell that this EEG data is of male and of 40 years old? Okay, so something like that. If you see, there are some smartphones when you want to take a photo and automatically it tells you that, okay, you look like 27 years old or 30 years old. Similarly, from this EEG data also, can I know that, okay, that he is this guy? I do not know. Okay, I do not see this guy, this face. But I, from this EEG, I will tell you that, okay, this is male and this is of 40 years old. How can you do that? Okay, so that's actually, it's a simple machine learning paradigm platform. Okay, simple pattern recognitions. So you will be collecting data from different users. Okay, EEG data you'll be collecting, and then you use some people things like noise removals and then feature extractions. Feature extraction that we have already discussed, and then you make some models like HMM models, HBM models, whatever models, and then given a new test data, you check with that model what is the class. Okay, very simple. So if you use, so in our experiments, so experiments are actually very important. If you consider that, okay, if I'm wearing this EEG device and I will go outdoor and then I will start, this will be giving me results. This is not correct. Okay, these are all in this lab-based setup. Okay, so this will not work will if you go to outdoor. So we have collected the data when the subjects are sitting in at relaxed positions and eyes closed. So in this system, for example, when the eyes closed and then we started closing, eyes closed, relaxed, and then we started the collecting the data from different persons. Different persons, like 60 persons we have collected. This distribution is shown here. So 6 to 10 years old of 10 guys, 10 persons from 6 to 10, 10 persons from 12 to 15. So this is the different age distributions and male and female. You see that this is not a regression problem. This is, we have used it as a classification. Like if you tell me, give me a data, I can say that, okay, it is of which category? It is of category 1, category 2, or it is of old age. Okay, older people, or it is very young, something like this. And we have used this emotive epoch plus 14 channel, 14 electrode device. Okay, it costs 1,000 US dollar. Okay, we bought it in 2017. That time it was 1,000 US dollar. Okay, so we have used this, for example, this hidden Markov model, HMM. So if we use this age and gender, so you get some accuracy with these different bands. I was telling this, you extract these different bands and then you extract some features and then you apply these classifiers, you get, we will get something which is the best accuracy here. We'll be seeing this best accuracy in gender. It will be some data, theta, delta, gamma features, frequency bands you collect, and then you you apply in this machine learning. You extract features and you apply classifiers. For age, this beta band will be better. Okay. You could also use LSTM, DLSTM, okay, deep learning models. So given a signals, so as you know, this in deep learning, you do not need to extract features. Okay, so raw data, if you can actually use this noise removal. Noise removal is better, so it will give you better accuracy. Otherwise, you have to do, the model should be very robust. You need to do a lot of training. So you use this BLSTM, LSTM, this deep LSTM, BLSTM layers to tell that whether what is the age and gender classes. Okay, so for example, if we are using simple LSTM, the accuracy, based accuracy is 96.35 for gender and 89.35 for age. Okay, so here it is also lower, okay, than this deep learning. But when we are applying this deep LSTM, BLSTM, means this, you have this more and more stacked, okay, this layers, LSTM, recurrent neural network layer. So you will be getting better results. The accuracy will be 97.5, and then recognition for age will be around 90.6 or 91. Okay. So this is one application where we have extracted the data from 60 different persons of different categories of ages and genders, and then we extracted the features that we have explained. I have discussed how actually we will be extracting the features, and then we use some classifier models, SVM or hidden Markov models. You will get the results. Details are there in this paper. Okay. Next, we want to use it, for example, for neurophone that I was telling that for interface, brain computing interface. So, for example, some patients are their brain is working, but he's not able to speak, or his hands cannot move their hands. So in such scenario, so if he just imagines some services he wants, so can I make an alarm, or can I tell him that, okay, so you are he's looking, this patient is looking for this service. Okay, so for example, I want the patients to imagine some of the symbols, some of the service he wants. For example, he will be imagining some music. He wants to listen music, or he wants to watch some movies, or he wants to call someone, Facebook, or he wants to play, or he wants to some service. Okay, some from the hospital. So if there are total 9 kinds of different activities are there, and each activity he can think of any of one of this. He can imagine. Okay, so for example, if he wants to imagine this plus symbol, he's imagining this plus symbols, and automatically we will get the EEG data, and then we will classify that he wants the service of this. He wants the service, okay, hospital service, caring service, or he wants to play music. So this EEG device, this 14 electrode device, it is actually connected by wireless. Okay, that is this flexibility is there. So he can actually, you do not need to be connected always with this computer. So we have used the similar things. Okay, so we have this EEG data. We are using this Fourier transform for this band separations. Then we have this EEG data. Then we extract some features. We use some HMM classifiers to access, to classify which application he wants. So now, if you see this all these 9 applications, the average performance is close to 69%. Okay, so each one you can see the performance, that if he is imagining of, for example, doctor service, this plus he is imagining, so 67% times we can classify from this EEG signal that he is imagining of this doctor service. He's looking for doctors. That's the neurophone. Okay, so we have called this as a neurophone. We can also use this EEG for authentications. Authentications, you know, this for example, this Aadhaar, for Aadhaar we have registered our data. Okay, so facial face image, signature, iris. Okay, so this kind of data we have given. It's for to identify myself or to verify. Okay, so for example, if I'm going later for some applications in this government sector, so they will check my Aadhaar ID, or they will verify whether these signatures or IDs pattern are same or not. Okay, whatever I have given in the beginning. So these actually, there are different modalities. So either you could use the signatures like in bank people do, or you could use iris data or palm print, or there are many. Now, the question is, can EEG, this brain signal, be used as authentications for authentication purpose? Okay, so can I, if I get a signals, EEG signals, can you know that whether this signal is from Partha Pratim Roy or not? Or can you say that who is that person? Who is the person who of having this EEG data? Identify or verify? Okay, so that is also similar to this biometric system in biometric systems. So I am giving one video, I'm showing one video. For example, here you will see that it is also with this emotive device that I was telling, 14 electrodes. So this, you see this, some of them are green, so you will get the signals. So this guy is actually wearing this device, and here the application is, so he is having this mobile, and for example, we are having this mobile, we make a pattern. Okay, and then if the pattern is okay, so pattern maybe it's A, Z, B, it's person to person varies. Okay, it varies person to person. Now if the pattern is okay, then it will be, he will be allowed, otherwise he will not be allowed. If for example, if my friend, he knows that I always make a pattern like Z or P, then he will also take my phone, and then he can make the pattern P, and then he can access. So that means this only pattern is not safe or secure. Okay, so can you use some EEG for this? Because EEG also can be used as connected with the wireless. Okay, so what we did, when we are making a pattern, okay, so while I'm making a pattern, so this is a stimulus. Okay, so I'm making a pattern visual stimulus, and that time how my EEG is responsive, how my brain is responding. Okay, so that actually I'm getting the signals. From that signals, so when I'm getting the signals, so for example, if it is my phone, I will register in my mobile or computer with some of signals. Okay, 3 to 4 EEG signals. And then given a new testing time, when I will be accessing, that time I will just check that whether my test sample is similar to my registered symbol, registered signal. Okay. So how actually we are doing? So from this training data, I make a model, and from this testing data, I just check that this testing data, how much it is closer. If it is if it is very close, means if it is more than a threshold, then it will be correct. Otherwise, no. Then actually, if it's genuine or false, so if my friend wants to make the same pattern, see, he can make the same pattern, but his EEG signals may be different. Okay, so he may be in a tension that he is using my mobile, so his EEG response, EEG signal will not be same like me. Okay, because he is having that fear factors or some other factors, okay, or stress factors. So that actually will allow not to match, okay, not to pass the thresholds or similarity matching. So there actually you can separate that who is the person. You can verify that who is the genuine person or not. But now, if you can say that, okay, if I'm making some A pattern and I'm making Z pattern, whether this will be same or not, yes, this will be different, because for every signals, every imagination, every activities, minute activities, all signals will be different. Okay, so for example, if I'm making Z pattern, so this will be different. If I'm making a something cross pattern, that will be different. This is the heat map. Okay, this is the heat map that which parts are active. Okay, in that brain when I do this, when I mark this pattern. So if I'm using HMM or SVM, then this according to classifiers, your performance could vary. So we have noted that because HMM is more for it fits more because it is used for sequential data. Okay, so that's why HMM is better than SVM, but deep learning will be better than HMM also. Okay, if you have more data. Then this is a we are using only this EEG for identifying or verifying. Now you can use this EEG for multimodal. Like in biometric, people are doing multimodal matching that only signatures will not work. For example, in banking setup, sometimes people check their photo and their signatures. Okay, so similarly in this EEG signals also, you can combine EEG signals along with your signature or face. Okay, so this could be used as combined with the multimodality framework, and you can get better results. For example, we have one system like don't just sign, use brain. That means when I'm just making a signature, okay, so when I'm making, so can I combine these signatures and EEG signals? Because when I'm writing something, that means my hand and brain are actually connected. Okay, so there I will get my signals. Okay, so according to my strokes, whether I'm making some ascending strokes like T, H, this kind of strokes, or I'm making some G, Y, this kind of strokes, or lower descending strokes. Okay, so according to the strokes, our signals will be changing. So these two informations, this stroke pattern along with this EEG pattern. So we can combine these two patterns to for authentication, like identifying or verifying. Okay, so this is actually a nice connections which could be used for multimodal systems. So we have seen from our experiment that actually this provides the better results than a single modality. For example, if someone same person is writing a different signatures like Mahendra or this signatures, so their signature will be different, their EEG signals will be different. Okay, if same person, if I am writing my signatures 2 times or 3 times, there will be also some changes, but these changes will be very less. Okay, but there will be, this will not be same. Okay, so even you are writing in the sometimes exactly the same information, it will be similar, but there will be some change because always internal stress, tensions, this will not be same. So there will be some reflections. So that I was saying that you actually extract the stroke information and you extract the temper EEG signals both together. Okay, so EEG will be generated according to the stimulus of the stroke. You are making some activity actions and that will stimulate your EEG brain, and that EEG you are getting, you are analyzing. So where you can will analyze the pattern. Okay, so whether this the writing stroke is ascending or descending. So this kind of information also you can pattern from this handwriting domain that I already told that. Okay, so you extract some features and from those features you use this RNN, and then from this EEG also you can extract some features and you can apply some RNN and you can combine. them together. So when you combine, so these combinations, combined modality will give you better results. For example, if you have this p-hog, we say that it is for signature from image data, and EEG is for this brain related data. So whichever is good, better, I can take this one for identifications. If you think that okay, this signature is better, so I can take. Otherwise, you can actually make a combinations. Okay, same weighted combinations you can do it. So you see this in these results that if I am using a simple image features, my results will be 85% results. If I am using 80 EEG, my results will be 5.65. Of course, EEG will be better than the signature because many people can mimic. Okay, so your signatures. Okay, so that means it's not so secure. But EEG is actually not easy to mimic, copy. But if you combine this EEG and this image stroke information together, you will get better results, 98%. Okay, so so that's actually this fusion. When if you combine this EEG with this, for example, facial part or signature part or IDs part, you will get better results. You can expect. Like that, you can do many other multimodal systems, biometric systems. Now I go to this another direction, that is the neuromarketing. Okay, so I have discussed about this some applications of this healthcare, one or two. Then I talked about this age and gender. Okay, so like with from EEG data, can we analyze EEG, gender, age information? I have also shown that from EEG we can identify and verify the person. Now I'll show to this another direction, that is neuromarketing. So neuromarketing is, for example, when these companies, they launch some products, they are interested that whether this product is really attractive or not, whether the customers, they are interested in that product. How actually they find this information at present scenario. In this present scenario, they only look in, for example, social media sites or YouTube based on the like, dislike, or comments, right? How many likes are there, how many dislikes are there, and whether the comment is positive, negative, or those. So comments means they analyze using some sentiment analysis. Okay, based on this analysis, they check that their product is good or not. But you can actually, this is not so realistic. For example, in some products you may not like, but you give very good rating. Okay, it may not be the actual reflection of what you perceived. So for example, I am saying that if my lecture is really interesting for you or not, you may think that okay, he's from IIT Roorkee, he's a good, so okay, so give 5 out of 5. But you may not like the content, or you may not like the presentation. So that means it is not realistic. Whatever you are thinking, so that's not coming up. So there, actually, this alternative approach is EEG is actually very appropriate, okay, effective. So whatever you are imagining in the online real time, these signals are passing, and it will tell you, it will tell the companies that whether the customers are interested or not. So for example, I'm just showing one video that, okay, so not video, it's a image that this user is wearing this device, and he's watching some products from this e-commerce websites like this Amazon, Flipkart, okay, so different products. And then he is, for example, these products are like shirts, shoes, ties, okay, these kinds of products. And then he has to mark that whether this guy really liked the product or not, yes or no. Okay, so that means he's watching the products in the monitor. That's actually visual stimulation. So visual stimulation, it will be reflected from EEG. So we collect the EEG, and then we also get the real picture, whether he has also said yes or no, like or dislike. Okay, so we have these levels and along with the signals. So if we have these different products and these different subjects, many subjects actually, they give the data, and then we can make a machine learning um, solutions. Okay, we have several data sets. We are doing the same things, feature extractions, and then classifications. And given a new test data, you also extract some features and you make a classifiers, and then you give a choice. Okay, so this is very simple, like whatever I have been telling. So you see, this different products would have this defined easy signals, and accordingly, heat map will be also different. Okay, so whatever he is watching, so his EEG signals will be different according to the product. If it is the same person, that is also it will be different. Okay, so now if we just use the classifiers, machine learning classifiers, you see that using this theta band, the accuracy we are getting close to 70%. Okay, 70% accuracy we are reaching. Okay, with this alpha band, the accuracy will be maximum is 68 or something. Okay, so you see that that I have already shown that every band will not give you show the results, because there are bands means they are actually in different frequency signals. Okay, so these frequency signals we are collecting, and then we are doing machine learning. Okay, so whichever is appropriate for that activity, that band, if you analyze, you will get better results. Not only that, you could also use, for example, this different region based. For example, I have shown you this in scalp, you can actually divide it into different regions like frontal, parietal, occipital, temporal. So so if I'm having 6 electrodes in the frontal part, so I'll just combine these 6 frontal parts electrodes and see their results. If I'm just using these parietal electrodes, what is the results? You see that except these occipitals, others are showing okay, so similar results, but I think this frontal is better. And then if you can combine, there actually you get a little better results. Okay, so there are actually many other works. So for example, you can also use them for sentimental, you can use them for sentiment analysis, like you collect the text informations from this YouTube or Facebook data, and then you check the positive or negative data. Okay, and then you can also combine in this from this EEG data. It's a single modality what we have shown, but you can also make it a multi-modality when you use this EEG data along with the textual data. So what text information he is writing. Okay, so this textual information also you can combine that from textual information, whether it is a positive sentiment or negative sentiment. Okay, so or also you can find that whether which brand it is. Okay, so you know that whether, for example, some persons are inclined to some brand. Okay, so it's a Sony product or it's a Apple product. Okay, so based on this brand value on this this textual informations, so these also information could also be combined, and you can get better results. Okay, so there are several data sets we have actually kept in our website. So for example, this envision speech recognition using EEG sensor, and then analysis of EEG signals and its application to neuromarketing. So this second one is for neuromarketing that I already explained you last. So these data sets is available in my website. And then another data set is, for example, I am imagining something. For example, we have this 30 plus problems like neurophone. Neurophone we have only 9 plus. Okay, 9 different services what we want. So in this actually we have kept 30 different um, 30 different objects. Okay, 30 different classes. So for example, 10 classes are of alphabets, numerals. For example, I am imagining A, 1, 2, 3, these kinds of alphabet numbers, or I have some I imagine, for example, lion, tiger, animals or cars, objects, these kinds of things. Total there are 30 class problems and different samples are there, each data are there. So these data are also available. Okay, so if some of you are interested, you can download this data and then you can apply your algorithm and see that whether you get better results. If you get better results, you can publish. And there are many data sets, many researchers also upload, you can also find. But in Kaggle, actually, you can find lots of data sets. Yeah, for them in deep learning, the last sessions also, whatever we have explained, there are many data sets. This ImageNet, all those are available in Kaggle, or for example, BCI data also. For example, here brain controlled spelling device for the completely paralyzed, or this exploiting elements and convolution neural networks with long short-term memory for classification of the human EEG. Okay, scientific reports. These data sets are also there available in Kaggle. So you can find more data sets and you can download. Okay, so some of them are available. Actually, in medical sector, some of these data sets are not available because of the privacy issues. Okay, so because of health related issues, so this health related data are mostly not available. But other data, people actually they can hide the user information and they can make them available. So thank you very much. So there are actually many papers we have worked. I have just shown you some of the glimpse of what we have worked, but there are many more. So you can find those work in my website. So I would like to thank these organizations which supported my uh, work and funded. So I was there in CBC, Spain, Barcelona, and then France, RFI Lab, Synchromedia, Canada. I worked in for 8 years in abroad, and then I worked in industry like TCS, Samsung. I am now visiting scientist in Indian Statistical Institute, Kolkata, and also in Japan, Osaka Prefecture University. I'm the visiting scientist. I have two students who are actually jointly doing PhD from Groningen University, Netherlands. I'm having projects from DRDO, then DST in Japan, Ministry of Education, Samsung. Thank you very much. So we can take your questions now. So that I was telling that you can actually search the papers, projects, data sets from this website, Parimal websites. You can find all the details, and you may always write me, connect me at this email ID, parthu@cs.iit.ac.in. Okay, so thank you. So let's see if you have any comments. Well, okay, so let's start with this figure from the beginning. Okay, so this RMS value for each signal, it's actually different. Okay, so it's based on the applications. So in some applications, see this, as I was saying, okay, as I was saying, this signals actually will change according to the activity or person to person. Okay, so this will be different. I could also show some practical with coding, but I do not have time now. But maybe in futures, I can show you some experiments where you can see the features and these classifications. Okay. Yes, that we have already discussed. EEG data available or not? That I have already discussed. Yes, yes, of course. When you will be making this EEG patterns, when you will be writing something or whenever you will be doing some excess activities, there will be some internal signals, okay, changes. These are actually noises, okay. These muscle movements, stress, some other tension. For example, you have taken money from some person. So always there will be some tension, okay. So you will be in stress, how to recover. So that actually everything will affect your EEG signals. But these are actually minute when you'll be doing some activity, and this is a pattern classification problem. So given some signals of 2 classes or 3 classes, the machine has to classify into these different space, different pockets. Okay. So if there are small changes, this will not affect. Okay, so with the small effects, this will not. But if you want to say that whether the signal is having muscle movements or not, that's actually 2 plus problem. Then you can say that, okay, this signal is having muscle movement, this signal is having not muscle movements. Okay, so like that actually you can classify. So you can have a very specific objective, whether this is a eyes move, eyes close, muscle, yes, no, writing, yes, no, different activities. So based on this, according to the objectives, you have these different pockets of the data, and then you given a EEG data, you just place. Well, yes, Gertz and Stephen, no. That time this EEG technology was not advanced and there was nothing. Okay, so there were no EEG based transcriptions. Okay, so I don't know how he could discuss, how he could interact, but EEG was not at all used that time. Okay, nowadays there are some papers from EEG. Actually, people are finding out the imagination or thinking, but before it was 10 years or 15 years back, before that was nothing. These are all latest technologies. It is for English. Okay, imagine speech dataset was for English 10 alphabets, randomly 10 alphabet we have considered. For example, it could be AM, it could be P something, and then 10 digits and 10 objects, total 30 plus. No local language. Okay, it's English. Any other comments? Yeah, thank you. Some of you appreciate it. Thank you very much. Yeah, given if some more time, actually more sessions, I could show this demo also. Maybe later we can show some hands-on. Okay, so how this EEG is actually, you can see the signals and those things. Okay, thank you very much. Yes, thank you, thanks a lot. Yes, hope these 2 sessions were useful.
Hello. Any questions from the audience side? Participants, any question?
Participants asked some questions. We have actually discussed those questions.
Okay, so it is already
And
discussed.
yes, we have already discussed.
Okay, I think no more questions from the participants. Okay, sir. Okay, then thank you very much. Both the sessions were very good, and even the feedback in chat box itself says that sessions were very good.
Yes.
Practical experimentation is discussed. So everybody is saying that both the sessions were very fruitful and they have gained so much knowledge from these. So sir, thank you very much sparing your time. In future also, we'll see if we can meet again for these type of.
Sure. Yes.
Sir, okay, sir. Thank you.
Thank you very much, madam. So yes, it was really honor for me to be here and have an interaction with you and participants. So
So in future, we will
these
have
are
some, physically, we will have some sessions. Virtually, we have met.
yes,
So physically also sometime when the
yes, sure,
ticket will be going back, then we will be meeting again.
sure, sure, sure. Okay, thank you, madam. Okay, so see you then. See you in future. So participants also, thank you very much. See you in future in some other forum. Bye.
Participants, next session will start at 2 o'clock. So kindly be here by 1:55.